All right, let's take a look at the proofs here. These can be really long proofs, or they can be really short, just depending on whether or not you apply the theorems from the unit. And luckily, we don't have that many theorems in this unit, so there aren't a lot of things you have to think about. All right, let's label our diagram here. BC is congruent to CD. Oh, look, it's an isosceles triangle, meaning this angle is going to be congruent to that angle. And then AB is congruent to AD. Oh, look, it's an isosceles triangle. That angle is going to be equal to that angle. And look at this. We want to prove that ABC is congruent to CDA. This is interesting. We don't even need congruent triangles to do this. We've already got the same markings on both of those. That's just going to be an addition property. So this could be real fast. So cannot stress enough. If you get two congruent sides in a triangle, immediately mark your two congruent angles. You get two congruent angles in a triangle, immediately mark your two congruent sides. Okay, it will make your life much easier in this test. So anyway, we're going to say that angle CBD is congruent to angle CDB, okay? And I'm going to say my one-step theorem in a triangle. If two sides are congruent, then the opposite angles are congruent, okay? Now, that is an isosceles triangle theorem. So if you struggle with that concept, if you're going to try to apply that to two separate triangles that aren't an isosceles triangle, then you might just want to say in two steps, triangle BCD is isosceles because it has two congruent sides, and then do an extra step saying that those two angles are congruent because the base angles of an isosceles triangle are congruent. Nothing wrong with that, but I like the short theorem because it saves me writing. All right, and it's going to be the same reason down here, right? We have two congruent sides, which is going to give us two congruent angles, so that's angle ABD is congruent to angle ADB. And it's the same reason, so I just put quotes here. And anyway, we're done, right? Because I can add congruent angles to congruent angles and get congruent angles. So we're going to say that angle ABC is congruent to angle CDA. And that's going to be an addition property, and we're just done. Now, be careful. You can't prove these two triangles congruent. It probably would have been better to draw the picture like this. It's really a kite, okay? But they don't say that any of these over here are necessarily equal to ones over here. Now, another alternate that people have done is to draw a C, and you can prove the triangle on the left congruent to the triangle on the right and get those two angles equal. So that's actually also a good way to do this proof. All right, let's take a look at another proof here. That was pretty nice. These are all pretty short if you apply the new concepts. All right, so CD is perpendicular to AB. I think it's going to be significant to have a right angle there. AE is perpendicular to BC over here. I'm going to go ahead and put those right angles in my proof. Angle CDA is a right angle if lines perpendicular, then they intersect at a right angle. Okay, and AEC is a right angle. Okay, and that's for the same reason. Now, segment AE is congruent to CD. Okay, AE is this segment here, CD is that segment there, so these overlapping segments are congruent. It's a little hard to mark that, but you just kind of have to remember it's that whole segment and that whole segment. So they want me to prove that I have an isosceles triangle. I have two ways to do this. I can prove two congruent sides, but I don't have very much about anything up here. Or I can prove two congruent angles. And I'm thinking, this triangle here looks congruent to this triangle here, which would show me that this angle is congruent to that angle. I think that makes a whole lot of sense, okay? And I think we have enough information to do this because the two overlapping triangles, and I'm going to shade in this one right here, they share side AC. So AC is congruent to itself by the reflexive property. And again, if you're having trouble with overlapping triangles, remember in the last chapter, one of the things that I really stressed was drawing overlapping triangles separately. So we've got ADC here, okay? We've got the right angles congruent. And by the way, you may need to say the right angles are congruent, but for hypotenuse leg, we don't need to, and I wasn't sure if what rule I was going to use yet. We have this side congruent to that side, so we have that side there, and then we have this shared side down here at the bottom, okay? If you notice, that's an angle followed by a side, and we don't have an ASS rule. However, we have hypotenuses congruent for the two triangles, sorry, hypotenuse is congruent. We have legs congruent. And of course, they're right triangles, so we have right angles. So this is actually hypotenuse leg right angle congruence. So I'm going to say that triangle DAC is congruent to triangle ECA by the hypotenuse leg right angle rule. Okay? And remember what we're trying to do here. We're trying to either get two congruent sides or two congruent angles. You could get AD congruent to EC, but you can't use the addition property to add these two things on to get congruent sides because we don't know that these two segments are congruent. But angle A in this triangle right here is congruent to angle C over in this triangle here. And that would give us two congruent base angles. And yet another reason you want to draw your overlapping triangles separately so you can see that those are actually individual angles of the two triangles. So I'm going to say that angle DAC is congruent to angle ECA. Those are corresponding parts of congruent triangles. Okay, and to close this out, remember, you don't have to prove two congruent sides for a triangle. You just need two congruent angles. So triangle ABC is isosceles. Remember, our book's wording is a little different. It says if a triangle has at least two congruent angles, then it is isosceles. And we're done there. Okay? Last one. We've got a perpendicular bisector. Now, you can do this as triangle congruence, and you can come in and say, okay, this is perpendicular, I have right angles here, it's a bisector of AC, that means AD is going to be congruent to DC, and you can do a bunch of congruent triangle stuff, okay? If you like doing 10 or 12 step proofs and that makes you feel good about yourself, awesome, okay? However, anytime I'm trying to prove a perpendicular bisector, or anytime I'm given a perpendicular bisector, I am thinking, can I use the equidistance theorems, okay? Because they're really powerful, they save you a lot of time, and a lot of time you don't have to do a bunch of triangle congruence proofs, okay, or steps. Anyway, so remember that we have a theorem saying that any points along the perpendicular bisector of a segment are equidistant from the endpoints of that segment. So if I have a perpendicular bisector here, this point is equidistant from the endpoints of the segment. And this point is equidistant from the endpoints of the segment. And this point is equidistant from the endpoints of the segment. And this is equidistant from the endpoints of the segment. And so on and so forth. And I'm looking at this, and I'm looking down my perpendicular bisector. You may want to highlight your segment that's being bisected here. Here is the perpendicular bisector. Okay? That means point B is equidistant from the endpoints of segment AC. Okay, there's one point. Point E is equidistant from the endpoints of segment AC. And so is point D. Okay? I think we only need the top two. So remember, we can just come in here and we can say AB is congruent to BC. That is exactly the same wording, at least according to our book, as saying that B is equidistant from A and C. And it's true because it's on the perpendicular bisector. So we got this great theorem that says if a point lies on the perpendicular bisector of a segment, then it is equidistant from the endpoints of that segment. Okay, it saves you a whole bunch of steps proving congruent triangles and showing congruent segments. Really, really nice. Okay, but if you don't memorize the phrase, you're not going to be able to apply it. Okay, also E is on the perpendicular bisector, so it's equidistant from the endpoints of AC. So that means that AE is congruent to EC. Okay, for the same reason, right? It's point on the perpendicular bisector, so it's equidistant from the endpoints of the segment that's being bisected. Okay, and we're trying to prove that BAE is congruent to BCE. We're almost done. They share side BE, right? BE is congruent to BE, and that, of course, is a reflexive property. And so the two triangles are going to be congruent by side, side, side. BAE can be congruent to triangle BCE by the side, side, side rule. So anyway, hopefully that gives you a nice example there of using that theorem. And again, if you want to prove a bunch of congruent triangles, if you want to say you got right angles here and you want to say that's a bisector, so these are congruent, you can get these two triangles congruent. And then once you get those two triangles congruent, you can get these two segments congruent. And you know, you can say this angle is congruent to this angle, and you can use the subtraction property and get these two angles congruent, and you can probably prove the two triangles congruent. There are all kinds of different things you can probably do. But again, I think the quickest and easiest way to do it is to use the equidistance theorem.